Hi, and welcome to a Calculus 1 video on continuity. And what's important to note is this is going to be the very basic idea of the definition of continuity and some things that you should know before heading into your calculus lesson on continuity itself. So when you get to that actual calculus lesson, you might see a problem that looks something similar to this, where you're given an algebraic function or piecewise function or something of that sort, and you're asked to discuss the continuity, or you're asked to make that piecewise function continuous. And we'll talk about that in the upcoming videos. For now, I'd like to go to a graph where you can kind of see what this looks like and what continuity actually means. So let's do that. Okay, so if I'm looking at this graph here, which is number 2, determine the intervals of continuity of the function below. What I'd like to make sure you see, the same things that I see, is that this function does not have arrows or points on the end. So if a function is meant to have a stopping point on the very left and the very right-hand side, what I'm just highlighting there, we would have to put actual points to denote whether they should be wholes or included values. So there aren't, so we can assume that those are meant to be arrows, because oftentimes some textbooks even leave off those important arrows. Okay, so that's one assumption I'd like to make. Now, the other assumption is, could you find from previous courses the domain of this function? So the domain was talking about all of the x values or input values that we have calculated on this curve. And this is a piecewise curve, right? It is a function. So what we will say is, if this is starting at negative infinity, because you always want to start left to right, I have all these x values that are included, and I don't have to pick up my highlighter here to draw it until I get to x equals 0. So what we would have said prior is the domain goes from negative infinity, and again, negative infinity is not an actual value, so that'll always have a parenthesis, comma 0, and since that's a whole right there at 0, 0, that is not included, so I will put a parenthesis. And we're going to go ahead and union that with the other part of my function, or the second piece of that function, which again starts at x equals 0, not inclusive in this case, and moving along, and I'll do this one in green highlight here. I don't need to pick up my highlighter or marker to keep drawing it until I get to positive infinity. So if you understand this idea of domain, that I have sort of this idea of a broken domain at x equals 0, or in other words, I had to pick up my pencil if I were drawing this curve at x equals 0. I have a jump or a point of discontinuity at that value. If we understood that from before, we're going to do pretty well with continuity. A basic definition of continuity, if I can, is, let's see, I'm going to give it kind of a three-piece here definition. I'm just going to say your limit, this is why it's a calculus discussion, as x approaches a some number from the left, so the limit of my function on the left equals, guess what, limit as x approaches a from the right of that same function. Now let me draw this scenario for you, and let's see if you can kind of poke a hole in sort of this only two-piece definition of continuity. So here I come along in some function, right? Doesn't matter that it's squiggly. If you don't like it to be squiggly, it can look like a parabola or look like whatever you want it to look like. And I could have a hole here, and I could go on up. Okay, so I could have some parabola. Now, as I come in from the left and I'm approaching some a value, let's pretend that this is x equals a, I have the same limit as x approaches a from the right. But any guesses of why I'm not continuous at x equals a? Well, I have to pick up my pencil and go around that point. I am discontinuous at x equals a. So my third sort of piece to this whole thing If the function truly is continuous, your left limit will equal your right limit. That means as you're coming along the curve, you're going to the same place from both sides, which also should equal your function's value at that x value, because then that's going to close in that point. Now you no longer have to pick up your pencil and you can just draw right over it, and you are one nice continuous curve. Okay, so I like to think of it as kind of a three-piece definition. Your left limit has to equal your right-sided limit, which has to equal your function's value. Okay, so if we take a look at this graph, whether you understand the definition in terms of calculus or whether you just understood the idea of domain, I can say, where is this function continuous? Well, it's continuous everywhere except x equals 0. So it's going to match my domain in this example, right? Everywhere except for 0, or if you think about it on a number line, going from negative infinity to infinity, everywhere except for 0 is going to look something like that. So negative infinity to 0 and 0 to infinity, and that might help you write out your interval notation if you need it. That is my solution there. If you are asked where are you discontinuous, you are discontinuous at x equals 0. Okay? So I hope this beginning discussion on continuity and domain will help you further understand it, so when you get to those discussions in your calculus class, they're a little bit easier to understand. I hope you found this helpful. Thanks for watching.